So hello everyone, I'm going to discuss about the various types of drag force today. So we're going to see about total drag and various components of what are the components involved in this total drag. So drag force is basically the aerodynamic load that tries to pull the object flowing through the air or at least passing through the air backwards. So what are the various types of components of drag that involve in pulling down the uh, actual object which is flowing through the air? That is our interest. So the total drag has many components. First one is the pressure drag. This is also known as form drag. And second one is the friction drag. And next, interference drag. And then wave drag. And also you have induced drag. Okay, so these all will involve in creating the total drag force on the object which is passing through air or say any fluid. So pressure drag and friction drag are combinedly known as profile drag. And profile drag and interference drag, these two things are again combinedly known as parasitic drag. Okay, so these are the basic things involved in the total drag. So pressure drag is something which is having again two components: high pressure at the front and low pressure at the back portion of the object. So whenever the object is flowing in this direction, say the air is flowing around it, so it will exert some pressure on this object and it will develop some high pressure area. So this will try to uh, push the object backwards. That is known as high pressure. And you have some flow separation region at the behind. So a vacuum will be created at the back portion of the object which is flowing through the fluid. So this is it's like kind of a vacuum. So this low pressure area will also try to suck the object backwards. That is known as low pressure. And another one is also there in this pressure drag, or also known as form drag, is that flow separation around the object can also cause drag. Flow separation generally occurs at the back portion as well as at some critical shapes of the object. We can generally observe at some top portions of automobile cars and on the hood portion and as well as the rear windshield portion. So this is about the general idea. And friction drag is something which is caused due to the fluid and body interaction, and this is where the boundary layer theory comes into picture. And friction drag is directly proportional to the thickness of the boundary layer. So if the fluid is flowing and as this object is uh, said to be stationary relative to the moving object, then you will have some boundary layer being developed. So you will have slow moving fluid. So this slow moving fluid tries to create some kind of frictional force on the surface of this object. So this is what known as friction drag, and this not only depends on the boundary layer but also on the surface roughness. So this is very important if you are trying to design a swimming suit or something like that, because the material you use greatly influences the amount of drag uh, being induced on the swimming person. And coming to interference drag, this is just a second. Coming to this interference drag, there are many expressions for this on the internet, but you can easily understand this as this is observed at critical sections. Say for example, you have object like this, okay, and the fluid is flowing in this direction, or in other words, the object is moving in this direction relative to the stationary fluid. So this air will have to first direct around this portion of the object and again at this portion of the object. Okay, I think you are understanding this. So again it also occurs here as well as here. So if there is also, I mean, there is also fluid flowing somewhere here, so this will have to again reorder, the flow will have to again reorder at some critical portions like this. So what will happen is it will try to induce some portion of drag, which is known as interference drag. So we can simply say that whenever there is a change in frontal area, okay, whenever there is some change in frontal area, you will observe this kind of interference drag. Okay, normal cars will have this type of body, and if you consider section at here, you will have one frontal area, and if you consider section at here, you will have another frontal area. So whenever there is some change, you will observe the flow redirection and flow rearrangement, that is causing interference drag. So what the modern designers are doing is they are trying to reduce the uh, sudden change in this kind of um, yeah, sections of the car. So they are trying to develop this kind of um, this kind of design. You can observe in Lamborghini cars, especially the hood and the windshield will look like a smooth curve. So they're basically trying to reduce this interference kind of drag. And coming to the wave drag, this is nothing but the shock wave drag. Okay, shock wave. Okay, so this is observed at supersonic speeds. Okay, supersonic speeds. So what happens is that whenever a bullet or a fighter jet is moving around and is moving through the air, then the fluid cannot understand that there is object here. So instead of directing this way, it straight away gets hit directly, because fluid understands that there is object only due to the pressure waves that the fluid tries to feel. So, and we also know that these pressure waves travel at the speed of sound. So if you have this object moving at higher speeds, then this fluid has very limited time to understand that there is object coming in front of it. So it directly hits the object and it causes shock waves like this. This is typically observed only during the supersonic and hypersonic speeds, and you can neglect this kind of phenomenon if you are considering normal automobiles. And supersonic speeds generally observed at 1000 km/h. Okay, supersonic speed is around 1000 km/h. So when you're designing supersonic aircrafts, fighter aircrafts, then you need to consider this wave drag also. And the last one is the induced drag. This is the most complicated part to understand as far as aerodynamics is concerned, but I will put it in simple way. Induced drag is caused only when there are lift or downforce creating objects, okay, basically wings. So there is some concept known as finite wing and infinite wing. In case of infinite wing, we observe that the aerofoil shape is infinite, and we basically consider the fluid as to be 2D. So when it comes to practicality, wing is basically a 3D object and it has a finite length. Okay, say this is the aerofoil shape. You have the finite length of the wing. So what happens is that at this critical edge or the tip, you will have vortices. Okay, you can study this on anywhere. This is known as wingtip vortices. But basically what happens is that, say you have low pressure area at the top of the wing and you have high pressure area at the bottom of the wing, and when it comes to the edge, there is no boundary here. There is no defined boundary to separate the high pressure region and low pressure region, and the fluid tries to enter from high pressure region to low pressure region, and there is also a straight moving component. So it will try to develop a helix kind of flow. It's known as tip vortices. And what these tip vortices do is that it will induce upwash in the mid span portion of the wing, and downwash portion at the mid span of the wing, center portion of the wing, and upwash at the tips. So try to see the normal view of this. So you have the wing. I'm looking from behind. Okay, I am looking from behind. You have vortices like this, and this is the wing. So this is trying to create upward moving fluid here, upward moving air, and downward moving air here. So this downward moving air, after the air has passed the wing, will try to modify the angle of attack of this wing. Okay, again I'm coming to the side view. This is the wing. Just a second. So we have the you have straight moving air like this, and you have some amount of downward moving air here. Okay, This is due to the downwash created by the tip vortices. So what this downward moving air at the behind of the wing do is that they will modify the effective direction of the air moving about the wing. So you have velocity like this at the front and you have velocity like this at the front. So the resultant will be something like this. Okay. If it is an infinite wing, it will be parallel to the flow, and if it is a finite wing, the effective flow of air around or about the wing will be get tilted towards this downward direction. So what will this do is that it will modify the actual angle of attack of it will reduce the angle of attack, it will reduce the designed angle of attack of the wing. So say for example the wing is somewhat inclined, it is having theta of angle of attack. Say if it is having theta angle of attack, and now the finite wing and tip vortices come into picture, and you have inclined kind of resultant flow. So this theta that is actually happening in the real flow will be lesser than this theta value. Okay, the angle of attack of this the real angle of attack of the wing will be lesser than the designed angle of attack. So now the wing is looking as if it is of 20 or 25 degrees, but in reality it will be only of 10 degrees. So what is this happening is that it is reducing the lift of this wing. It will reduce the resultant lift force acting on this wing. So in order to compensate for the loss of lift, okay, I think you are trying to understand, whenever there is a reduction angle of attack, there will be loss of lift force. So to compensate for the loss of lift, we will have to put the wing in much more inclination. So as we have discussed earlier that the effective angle of this wing has reduced from 25 degrees to 10 degrees, say in this particular example, then you will have to again raise the angle of attack to 25 degrees. So in reality the wing could have been even more inclined. So if you put the wing at this such a high angles, what will happen is that the drag force is also going to increase. Okay, because the lift force acting on this wing is in inclined direction. It is no more perfectly vertical, but it will be somewhat inclined. This is the resultant lift acting. So this resultant lift will have again two components. One is the vertical component, and the important point of this, I am finally coming to the point known as induced drag. This component is going to create some sort of component horizontal to this flow. So this component is known as induced drag. Finally I came to this point. Okay, induced drag. Okay, so because of we have a finite wing, and because of the presence of wingtip vortices, we have a loss of lift, and to compensate for that we have increased the angle of attack of the wing further, and we have inclined portion of the resultant component of the lift, and we also had, due to this effect, we had horizontal component also. So the lift is inducing a kind of drag on this object, on this wing. The lift force is inducing a drag component on this wing. So this is known as induced drag. Okay, I think I have covered all the types of drag forces. So induced drag will be there only when you have some finite wing. Of course, research is going on now to uh, reduce the effect of this induced drag by developing wingtip devices and those things. Something known as aspect ratio. Many things are going on now, but As far as basics of drag is concerned, this is sufficient for me. And thank you very much for watching this video. And please do like the video if you really like it. Thank you.